Well, hello, and welcome to another episode of Quantitative Bytes. It's great to see you all here. Today, I must admit, I was going to start looking at fractals using turtle graphics, but when I really started to come to put that video together, I realized that it would become excessively long if I put everything together, because actually there are some changes that we need to make to the turtle class that we created in the last video before we can actually go on to look at using it to make fractals. So what I want to look at today is to quickly go over the changes that we need to make to the turtle class, and then in the next episode we will actually start looking at how we can go on to use that to create some fractals and to start explore a particular class of fractal objects, which hopefully will be interesting. As always, if you like this video, please do remember to hit that like button, and please remember to subscribe to my channel if you haven't done so already, so that you don't have to miss any future videos. Okay, so what we're going to do today is in the last episode, let's just quickly recap the last episode. I'll put a link on the screen up here, I think. And so in the last episode, we created a class that allowed us to do basic turtle graphics in C++. So we had this turtle object, which was not visible, but we could then give it commands like move forward, turn left, rotate right by a specified amount, and so on. And we could use that to draw lines, to trace out lines as it went. And we showed how we could use that to create some rather interesting patterns and effects. The one extra method or function that we need our turtle to have is the ability to point at a specific, to look at a specific point on the screen. So what I mean by that is we need to be able to specify X and Y screen coordinates and then tell our turtle to look in that direction. So that's different to simply specifying the angle. So with the functions that we gave our turtle before, we could make it look in any particular direction, but we had to specify the angle ourselves in degrees. So that's not quite the same thing. What we want to be able to do is to specify a position on the screen in screen coordinates, and then have the turtle automatically calculate the required angle and rotate to face that point, so that when we then make it step to go forward, it will move towards the point that we told it to look at. So that's what we're going to do. To begin with, I just want to start with a quick explanation of the geometry of this, actually, because it's a little bit interesting, and it's one of those things that you think is going to be, oh, that's going to be so basic, but it's actually a little bit more subtle and complicated than perhaps you might think, which is one of the things that makes it quite interesting. So we're going to have a look at that first. Let's jump to it. So this is the hypothetical situation that we're talking about. So the object here in the middle, this is my best attempt at drawing a turtle. I'm sorry, it is slightly better than the effort I made in the previous video, I will admit, which was just an orange square, and now we have a blue square which broadly has a head and 4 feet, so it is a little bit more turtle-like. Anyway, the turtle is positioned in the center of the screen. We have our x coordinates, x and y, and for now we're going to consider the center of the screen to be the origin. So 0, 0, x 0, y 0 is here. Y increases going up, x increases to the right. And what we want to be able to do is to calculate the required angle by which we need to rotate our turtle to look at any specific point on the screen. So that's really basic, you would think. So our turtle is positioned here, this is the origin, and then we have our point that we want to look at, which you said is at coordinates x equals 1, y equals 1. And then we have our angle here, theta, to the x-axis. All we need to do is to calculate that angle of theta. Well, that's basic trigonometry, isn't it? So theta is equal to the arctangent of the difference in y, the change in y, divided by the change in x, which I call dy by dx. In both cases, dy dx is 1 and dy is 1. Therefore, theta is equal to the arctangent of 1, which gives theta equals 45 degrees, which is exactly right. So over here on the left, I've created a section for the pseudocode for what we're going to write. Now in this scenario, that's really basic. We just know that theta is equal to the arctangent of dy by dx. Nothing complicated about that. However, the first complication arises if we have this situation. What happens now? So now the point that we want to look at is directly above the point where we are already. So the new x position is 0, and the new y position is 1. If we plug those coordinates into this equation, theta equals the arctangent of dy by dx, well, dy is 1, okay? so that's fine. But dx is now 0, which means we have that theta is equal to the arctangent of 1 divided by 0. Now, of course, anything divided by 0 is either infinite or undefined, depending on your viewpoint. So what do we do? So theta equals what? Well, okay, so in this situation, we can't use this equation to calculate that, but we know that theta is 90 degrees. Okay, so this angle from the horizontal axis, from the x-axis here, is 90 degrees. Okay, so similar situation if we go the other way. So if now delta y is -1, so we're now looking at a point directly below the origin, well then it's the same thing. Now we just have -1 divided by 0. Well, that's still undefined. So both of these cases we need to look at separately, but we also know that the angle here is now no longer 90. Okay, it will be 90, 90, 90, or 270 degrees, okay? So we can now write the pseudocode for that. So now we have, in our pseudocode, we now have a check. We check that if dx is 0, so if the change in x is 0, so that means we have either of these two scenarios, then we check if dy is positive. If it is, then we set theta to 90 degrees, okay, there we are. And if dy is negative, then we set theta to 270 degrees, which gives us that angle all the way around to there. If dx is not 0, so this is the else statement here, then we know that theta is equal to the arctangent of dy by dx. Okay, all pretty simple. But what happens if we have a point that's over here? So in both of these two examples, what we've done, we've just focused on points that are in the positive x half of the plane. What happens if we have a point where effectively where dx is negative? And the reason that's slightly complicated is if we have x of -1, y of 1, so we have dx is -1, dy is 1, then simply have, following this equation, theta is equal to the arctangent of dy by dx, and we know that theta is equal to the arctangent of 1 divided by -1, which gives theta as -45 degrees. Now, this angle here is not -45 degrees. -45 degrees gives us this angle here. So if we simply use this pseudocode that we had before, we simply drop down to here, we would calculate theta as the arctangent of dy by dx, and that would give us a point here, which is obviously incorrect. So we need one final line or section to our pseudocode. We need to check that if dx is less than 0, then we add 180 degrees to our angle of theta. So in this case, we get theta equals -45. That puts us to here. And then we add, because we know that delta x is 0, we now add 180 degrees to that, which brings us to here. So we will end up with the point where we want it to be. Okay, so that's a very quick view just of the basic geometry. We've sketched out our pseudocode. So let's have a look at how we would actually implement that. So I'm going to start in qbturtle.h. This is the code that we developed in the previous episode. So I'm just building on the code that we made from the previous episode, and we are going to add some new functions to our turtle. So first of all, we're going to put these in methods to control movement. So we're going to have a new function here, which is going to be void LookAt. So this is the function we're going to call to instruct the turtle to look at a specific position, which we're going to specify by float xpos and float ypos. Okay. Now I'm also going to add methods to allow the user to retrieve current position. So these will become very useful in the next episode, but we're going to do those. So we'll just have float get x and float get y. Okay, really basic. So let's save that. And then we're going to jump into qbturtle.cpp. Okay, and we're going to add the new code that we need. Now we're going to put it in. It doesn't really matter where we put it, but we're going to put it above the step function and below the rotate left function. Okay, so we just defined the prototype already. So this is qbturtle : LookAt, and we know we accept float xpos and float ypos as our inputs, so you don't need a semicolon. Okay, so we're going to follow the pseudocode that we just wrote, basically. So we define delta x is equal to xpos minus mx. Remember, mx is our member variable that stores our current location, and our dy is ypos minus my, just like that. Now, following our pseudocode, we check that if dx is equal to 0, okay, then we check if dy is greater than 0, like so. Well, in fact, let's not write it. Let's not use the curly braces there because we've only got one line. So if dy is greater than 0, then we know that m angle is equal to m pi. Let me just check that I did include already math.h. Yes, I did. So m pi, of course, comes from math.h in the standard libraries. In this case, so if m pi divided by 2, of course, we're using radians here. Okay, so if we look back at the pseudocode of what we're doing, so we're in this section. So pi divided by 2, of course, is 90 degrees. Okay, so this is the pseudocode that we're following here. Right now, if dy is not greater than 0, then we set m angle. Now I've written this out as m pi plus m pi divided by 2.0. I've written it that way just because I think that's a little bit more clear. That's my personal opinion. Okay, and okay, so if dx is not equal to 0, then we know that from our pseudocode that we calculate the angle as being the arctangent of dy by dx. Really simple, and that's all that we need to do there. And then the final bit of code, just to, if delta x dx is less than 0, okay, then m angle plus equals m pi. Okay, and that is it. That is everything that we need. So we save that. So that was qbturtle.cpp. We just defined this new code here that allows us to specify a point on the screen that we want the turtle to look at, and this calculates the appropriate angle that the turtle has to be rotated to and stores the angle, so we don't need to worry about doing the rotation. Okay, now finally, just right down at the bottom, I'm also going to add float qbturtle : get x. Okay, this is really simple. Simply returns return mx, like so, and float qbturtle : get y, exactly the same, return my. So like I say, when we actually come to look at how we're going to use this to make fractals, the reason for having those will become obvious. Okay, so that's actually everything we need to do in our turtle class, so I've gone ahead and saved those changes. Now, the next thing that we need to look at, we need to do something to actually implement that to show that it works. Now, before I do that, though, I wanted to make one other change. So I realized when I did this code before in the previous episode, I specified a predefined list of colors that correspond to the blue, orange, and yellow colors that I use for my channel branding. And then we created a system to simply loop through those colors as we drew the shapes, which created an interesting effect. But I realized that the way that I defined the colors using std vector and then manually pushing the values into them was really not the smartest way to do it. So we're going to replace that. So let's just delete that section of code. What we're going to do instead is std : array int a size 3 and m red list, like so. Now we're going to simply define our red values of 51, 255, and 255, and those are pre-allocated, so we're using the curly braces for that. Okay, so std array, and in fact, yes, let's finish that first. So int 3m green list, okay, which gives us 128, 128, 191, okay, and std array int 3m blue list. Now the reason why I've put those tabs in there, I'm hoping will become obvious now. 0 and 0. Okay, and let's just tab these out as well. Just like to make everything nice. Okay, so the reason there that I've put those tab spaces in is so we can see clearly what the colors are. So the first color is not 51, 255, 255. The first color that will be used, of course, will be red, green, blue. So it's 51, 128, 204. And then we have 255, 2180, and 255, 1910. Okay, so let's save that. And then we go back to capp.cpp. We need to make a little bit of a change here. So right up at the top here, we pre-calculated those. So originally, here we go. Yes, So originally this is how I defined those values, and it was in the constructor function of CApp. We no longer need to do that, so we just delete those and just get rid of that. Okay, and now actually we can simply loop through the colors in exactly the same way. We don't need to change anything because of that. But what we do want to do is to create something of a new demonstration now of our new turtle capabilities. So what we're going to do is let's delete this block of code. So this was the block of code that drew the interesting shape from the previous episode. So I'm simply going to delete that. Okay, and we are now going to test the turtle LookAt function. Yes, function, just like that. Okay. Now, I am first of all going to increase our length here to 150. Right. Now we're going to need to define some positions that we want our turtle to look at, and of course, since we want to test more than one at a time, we might as well define those as arrays. So we create std array of type float with 8 values called x target. So these are the x positions we're going to look at, and these are going to be 0, 320, 640, 640, 640, 320, 0, and 0. So if you just think about what that means, so 0, this is going to be the point that corresponds to the top left corner. In fact, let me put the y coordinates in as well, and then hopefully it'll be more obvious. And y target we define exactly the same way, but this will now be at 0, 0, 0, 240, 480, 480, 480, 240, just like so. And what we could do is just tab those out a little bit just to make things, well no, I'm not going to do that because it just makes it all look a bit method. So the first coordinate that we're interested in is 0, 0, which is the top left. Then we have 320, 0, which is going to be the top middle, and then 640, 0, which would be top right. Okay, and then we have 640, 240, which is right middle, and 640, 480, which is bottom right, and then 320, 480, which is bottom middle, and then 0, 480, which is bottom left, and 0, 240, which is a left middle. Okay, so now all we need to do is to loop through those, and we can make our turtle look at those different positions. So we can do that very simply for int I equals 0, semicolon I less than x target dot size, simply makes it a bit more generic, semicolon plus plus I, like so. Now inside this loop, we are, each time we go around it, we want to move the turtle to the center, 320, 240. Now the reason we do that is because if we didn't, it would simply draw from the end of each line every time, and we want it to draw from the center. I'm going to do mturtle.set pen color, oops, mturtle.set pen color, and now we go for m red list, I modulo 3, m green list, I modulo 3, and m blue list, I modulo 3. So that will loop through the 3 colors that we've defined, and of course we need to specify an alpha of 255. Okay, and then we have mturtle dot, we're going to call our new method now, the LookAt method, and we want to look at x target I and y target I. So that will loop through these coordinates that we've defined here and look at each one in turn. And finally, we need to make the turtle move using the step method. Say, okay. That is actually everything that we need to do. So we've changed capp.h just a little bit so that we define our predefined colors in a more sensible way, and we now define them in the header file, so we don't need to worry about it in our CPP file. We deleted the code from the constructor that we had written before to pre-allocate those colors, because that wasn't the best way of doing it. And now we have created this code here that defines 8 pairs of coordinates corresponding to the 8 coordinates around the edges of the screen, and we've created a loop that will loop through all of those, and each time it will position our turtle in the center of the screen, set the pen color according to our predefined color list, set the LookAt to be one of these coordinate pairs, and then we'll step the turtle to draw a line. So let's make sure everything is saved, and we're going to go back to our terminal window. Okay, here we are. So So I've already got all the functions that we need here. So we're going to compile everything. We're going to use g++ -o main, because that's the name of the executable file that we want to create. We're going to compile main.cpp, going to compile capp.cpp, and we're going to compile qdturtle.cpp, and we need to tell the linker to link against the SDL library, which we do with -l SDL2. So if we run that, oops. Okay, I've forgotten, I've used array here, and I forgot to include it. Okay, yeah, so we also need to include math.h as well, because we use the modulo operator. So at the top of capp, apologies about that, at the top of capp.cpp, we need to hash include array, and we need to hash include math.h. I think probably I get that from the header file, but never mind. We'll include it there, it won't hurt. And okay, so if we go back to our terminal window, let's clear that, rerun our compiler. That should all work now. No, it's in capp.h. Oh yes, of course. Oh, I'm so silly. Okay, but look, that's a really good point. I'm glad that happened, because it really allows us to demonstrate the importance of that. So here in capp.h, we had previously hash included vector from the standard library, and we need to change that to array. Okay, so if we save that now, we should be in business. Okay, I think it's a positive thing when errors happen like that, because it creates the opportunity to emphasize certain things. Okay, so if we run our compiler now, okay, now everything compiles properly, and let's have a look at what we get from our output. And there we go. Okay, our colors are not exactly right, but what we do see is that we get exactly the result. So this is pointed towards every corner. So it's pointed to 0, 0, and then it's come back to the center, and it's pointed towards the upper middle, and then upper right, and then right middle, and lower right, lower middle, lower left, left middle, and oh, that was the end. So we can see that that is all functioning. I just am actually very slightly concerned that the colors are wrong. I just want to have a look at that. It's not the most important thing in the world, but they should be right. So what's the matter? Yes, of course, not 218. 128, there we go. Yes, 255, 1280 for the middle column there. Save that. All right, not a big deal, but if we compile it again, and rerun our code, and there we go. Now we have the proper colors, which does make things a little bit more obvious. So we can see from a very simple test that what we've done is created a method for, or a function for our turtle class that now allows us to specify at any point anywhere in the screen coordinates, and we can use that function to make sure that the turtle points in that direction. Now the use case for that is not going to be obvious right now, and this isn't a particularly exciting visual effect. Apologies about that, but it is actually very important, and like I say, the use case for it will really become obvious when we come to look at the next video. So yeah, so there we go. One thing I mentioned just very briefly, so if we go back to capp.cpp, and I mentioned in here that we need to move to the center position every time. If we don't do that, let's just have a look at what happens. So if we put move to the center outside of the loop, and then if we just comment that out, there we go, and save that. Let's run our compiler. Oh, I'm still running my code. Let's quit that first. Okay, close that first. So run our compiler again. And rerun our code. And yes, so this is the effect that we get if we don't reset the position to the center every time. I just wanted to demonstrate this because it's more powerful than me simply talking about it. So what happens is we start from here and we instruct the turtle to look at the top left corner, and then we call step, which moves it to here, and then we instruct it to look at the top middle and call step, so it moves then 100 units in this direction, and then we tell it to look at the top right and call step, and it moves 100 units there, and then we tell it to look at right middle, and so on. And I think you can see the pattern, and that does produce that effect, which is arguably perhaps a little bit more interesting than the image that we had before. But yes, I acknowledge still not terribly exciting, but really important. So that's actually everything I wanted to talk about today. Now, I know it's a very short episode, and I know that what we've done doesn't perhaps seem visually very exciting, but it's quite important to get that out of the way. And like I said, for the next episode, when we start to come to look at actually generating fractal curves with the turtle class, then this function that we've added today will be really very important. We're going to make extensive use of it. And like I say, I did originally look at doing this all together with the content for the next video, but it just made it too long. And so I thought it better to make a short video about this now and then get this out of the way, and then we can actually focus on the much more interesting stuff in the next video. Anyway, that's really everything I wanted to talk about today. So as usual, if you've liked this video, please remember to hit that like button, and please remember to subscribe to my channel so you don't have to miss any future videos. Listen, it's really been a pleasure. I really hope you've enjoyed it, and I really look forward to seeing you in the next video. Thank you very much for watching. Bye.